Welcome back. This is the last part 6 of session 5. We are still talking about data representation. I want to reiterate the pipeline. The pipeline, and I want you to remember that all the time in every slides that we discuss or you do any project. One is the data. How is the data represented? Then you're going to clean the data. How do we clean the data? I'm going to talk about that in the next series of a slide. Then you're going to start processing them. Then you're going to actually visualize them. So you need to remember this pipeline all the time, okay? Let me share my screen and begin the discussion of the voice and signal representation. All of this come to you naturally because in your 2 decades of life, assuming you are 20 years old, you have heard many voices. You have seen many images. So when we get to this stage of the education and training, you need to be able to identify the voice that you have heard. Your voice, the voice of your friend, the voice of a waterfall, the voice of a stone breaking a glass. You need to be able to understand them. Now, you are human. And because you're human, your brain can actually process that without even telling you about it. Kind of autonomously, the brain is processing everything. But that's not it. You are now talking to a computer. And since you're talking to a computer, you need to actually be able to represent and identify the signal for the computer benefit. Now, when we talk about the signal representation, we have a waveform representation. I'm going to show you an example. We have a spectrum representation, and we have sonogram representation. These are just a few. Don't get me, don't assume that we have covered all of the keywords and all of the representations in this short slide. As you can see, the slide was supposed to be 74 pages, and I had to cut them down so that we are going to keep it as simple as we can. Now, when we talk about waveform representation, it is going to have an axis of time. This is potentially second, 0.01 up to 0.06, possibly 0.07. So the time is x-axis, and the amplitude is actually shown on a vertical axis. And the amplitude, you could define what that amplitude means. The amplitude could potentially be the velocity, meter per square second. The amplitude could potentially be displacement. The amplitude could be the volume of a voice. When you are listening to a music, the volume of the voice could potentially be your amplitude. We call it amplitude to generalize that vertical axis in. So what happens is that if I ask you to listen to the heartbeat of a child, of your mother heartbeats, or if you want to listen to a music that is of favorite to you, or what is happening, you're actually spending time, and the music is going to go high and then low in terms of amplitude. And you can sketch that in a 2D graph. You can potentially visualize that. Your heartbeat, for example, generally speaking, if I wanted to use the heartbeat example, let me grab an example here. I'm going to say heartbeat signal. This is a heartbeat signal, right? So take a look at this. And the heartbeat signal is really like this. This is my heartbeat signal. And it has a specific pattern. There are different components of a heartbeat signal. And as soon as you enter into that domain, biomedical engineering, biomedical science, you're going to identify different types of signals in this complex repetitive signal, okay? That's one example. You could potentially have a music signal. So let's have another example. So in another example, basically I wish I had a better signal. This is not bad. This is a function that is available. Maybe I want to have dolphin, and that's the dolphin sound. This is the dolphin sound, and it's not the same as heartbeats. It's not the same as human voice. It's a different time altogether. So actually what I'm showing you right now, it may not be in time, it may be in a spectrum. So we have in time, and in time is actually the amplitude, and the amplitude is defined by you. Okay. Now, in terms of a spectrum, and that's what I was just showing to you, perhaps, is that you are going to look at different frequencies. Frequency, you don't have to be expert in signal understanding. You have low pitch, high pitch, medium pitch. I'm sure you have heard of that name before. Pitch. Pitch means frequency in this case. So if you take a look at the same signal in time could potentially be represented in terms of frequency. So when I say 1000 hertz, 1 kilohertz, I'm going to have 1 kilohertz. 1 kilohertz means every second I'm going to have component that is going to be repeated 1000 times in every second. That's 1 kilohertz. When I say 2 kilohertz, in every second I'm going to have 2000 repetition. Now, all of these little cosine functions. So if you take a look at the, I might as well take a look at the spectrum signal and see if I can show you a breakdown. So this is actually not bad. I want to show you this one. This is not bad. So I do have a cosine function per frequency that is going to tell me how many times per second these peaks and throws are going to actually repeat themselves in a given second. I could potentially represent the entire signal that is going from minus infinity to plus infinity in only 2 pitches on the frequency domain. We don't want to go into the negative domain. We want to go into the positive domain. So this is kind of the frequency of the entire time domain signal. Okay. If you take a look at this one, again, once again, you need to consider that there is an axis here, and this axis is a mirror, allowing us a mirror representation of the frequency component. You have almost 60 hertz. And when we call it actually, if 50 is the axis, this is going to be plus 10, and this is going to be minus 10. This is going to be plus 40, and this is going to be minus 40. Let's ignore the left side of the axis, the vertical axis, and focus only on the positive side. So basically, as you can see, this signal has two predominant cosine functions. This is one here, the amplitude is here, and the power perhaps, or the amplitude, as well as another one here, and those are going to be perhaps insignificant. When you take a look at a stock market signal, so take a look at a stock market signal, signals, the stock market signal are quite fast if you zoom in. So therefore, they have high frequency components, day trading or high frequency trading anyway. But if you zoom out and if you take a look at that, you can see that this is going to be slow moving. So when I zoom out, I'm actually going to take out all of the rapid changes, and I'm going to only have something like this, just a small movements of the signal, and that's going to be representing my signal. My stocks. So what am I interested in? You might say, listen, why don't you go from time domain into frequency domain? Let me show you what I mean. So why don't I go from time domain, which has so many amplitude, into frequency domain, and then make a decision. And the decision is, listen, let's ignore all of these. All of these are too small compared to the amplitude that I have an interest in. You could potentially say, I'm going to be interested in this area only. So I'm going to be interested only in this section. and only in this section, and I'm going to ignore everything else. You could even have a kind of a ratio in mind, 1 to 10. So I'm going to say that this is 10 times, 20 times more powerful compared to this. Why? Because if you take a look at this signal, there are lots of changes that may not be necessarily useful and or even helpful in the process. Because sometimes too much of a noise is actually going to mislead your machine learning algorithm. So this is frequency-based representation. The x-axis is going to be frequency. Again, 1 hertz means 1 period of the signal for 1 second, 1 hertz. When you say 1,000, 1,000 of maximum, minimum in 1 second. So keep that in mind. Those are little cosine components, and these are the significant ones. Once again, you can have the same amplitude going into the frequency domain. You need to define that kind of a signal. Now, a study has shown that in many occasions, you can't just rely on time, you can't just rely on frequency alone, you have to have a combination of both. So for a given time, you could potentially identify, so I'm going to go back, for an example, I'm going to just have a small window. So if I could potentially, this is my window, right? And in that window, I'm going to find what my frequency components are. I'm going to go into this window and find my frequency components there. I'm going to go into this window. I'm going to find my frequency component there. If you do that, you're going to create what we call a spectrogram representation. It's amplitude, time, and frequency. Time is potentially x-axis, frequency is going to be y-axis, and the intensity is going to be the frequency that you're looking for. So I would say at 0.4, the intensity of the frequency is here. At 0.2, potentially the intensity is going to be here. I could potentially decide which time window is significant and make it potentially my own judgment, and my own process and my own algorithm is going to be dedicated to that process. And speaking of stock market signals, although they intend to repeat themselves, they do not repeat exactly the same way that they are. So you could potentially want to find some sort of a similarity in the past, correlation, covariance, convolution. You want, sorry, not covariance, convolution. You want to find here versus an event that has happened in the past. For example, the time when the quarterly results were released. So that's a very specific time frame in your mind. Quarterly report released, and then you want to see what happens to the stock market. It's going to rapidly change. And then when there is no news of the stock is going to be swimming in a silent, peaceful sea and ocean. It doesn't really move rapidly. There is no negative news. There is no positive news. It's just going on a sideway. It's just playing by itself. Are you interested? You may be. Are you interested? You may not be. It all really depends on what your intentions are. Humans, generally speaking, would understand between 20 hertz and 20 kilohertz. Elephant would understand anything below 20 hertz, and bats and dolphin, they will be able to actually see the high pitch, the above 20 kilohertz. It is also very important for us to actually do windowing. Windowing in time, it could be windowing in frequency, it doesn't matter. The style and the approach is the same, and the meaning could be significant depending on how you are going to. Now, if I had a speech, and in the speech I want to say, go and see a doctor for COVID-19. COVID-19. So when I say COVID-19, everybody is going to pay attention to me. COVID-19 is the buzzword these days. So you want to grab what is called COVID-19. Among many things, many words that I have said, I'm just talking to you. And this talking to you is a time signal versus an amplitude. Talking to you, talking to you, talking to you, talking to you, right? So you can see my amplitude is actually fluctuating. And when I say you really need to see a doctor for COVID-19. So what happens is that your ear, your brain is actually going to have a window on the signal. And that signal, COVID-19, has a specific characteristics in mind. it has COVID-19. So obviously, there's pronunciation, even if it is males and females and genderless base, whatever it is, COVID-19 is has a very specific components inside. So I should be able to actually grab exactly the COVID-19 from the sentences spoken in the room. So for us to do that, we have two types of windowing. One type of windowing is kind of a cosine function. This is a kind of a normal function, bell curve, I would say, but most of the time we call them cosine windowing. So this is a cosine windowing. This is part of a cosine function. And as you can see, we are decreasing the significance of the signal here. We are decreasing the significance of signal here. We are amplifying the significance or capturing the significance of the signal in the middle. We are actually killing down everything else. Go and see a doctor for COVID-19. I don't want to hear go and see a doctor for. I don't want to hear anything. I just want to hear COVID-19. And even in COVID-19, I want to minimize the entry to the statement COVID-19, and I want to minimize the exit to the statement of COVID-19. I really want to know COVID-19. So this is going to be a part of my filtering process. This is a window. I could potentially have a square window. A square window is as simple as what you see right now with all the cases. So this is my square. So I'm going to actually create a square if I could. Let's see. This is my square. Okay. Okay. So let's see. That's a square window. As you can see, everything behind is killed, zero. Everything after is filtered out, and only the entire intensity of COVID-19 is going to be captured. You need to be aware of these basically terminologies, these data representation. And when we go to the next stage, as soon as you have collected the data, your job is going to be to clean the data, to start to make the data ready for processing. And that's what the next slide is going to be. Thank you very much. Session 5 is now over.